Okay. What is the probability of getting odd numbers on both dice when we roll a pair of dice? Well, you can write out that sample space if you want. It's a quite large sample space because I think we did it earlier in another chapter. But let's just think about this. All right, so odd numbers on both. Let's just write those out. What rolls here of the dice would have odd numbers on both? Well, we could have, of course, 1 and 1. Just kind of do it in order. We could also have 1 and 3, 1 and 5, with the 1 first. Okay, then we could kind of adjust that a little bit. What if we have a 3 on the first one? Well, you could have a 1 on the second one. Now, again, kind of like the coin problem, 1-3 is different than 3-1 because this is 1 on the first, 3 on the second, right? This is the other way around. All right, so that's a different one. All right, what else could we have? Well, we could have 3 on both. Then we could have 3 and 5. Maybe see what's happening here. Then we could have a 5 on the first. Well, then it could be a 1 on the second. 5-3, 5-5. Any others?
No.
Good with that? All that? Odd numbers on both?
Mm-hmm.
Samantha, you good with that? Isaac, you good with that?
Good.
All right. All right, so now, what is the probability of odds on both? Well, we've got a total of 9 here. Now, we just have to figure out how many there are. So if we go,
36.
yeah, if you think about what we did, when we did it, we kind of did a table where we did the 1, 2, 3, 4, 5, and 6 along here, and then the other one. Remember doing that?
Oh, yeah.
We did the table. And so all together, yeah, there was 36. 36 possible there. Now, again, does everybody see where we got those? So, yeah, that reduces, we can reduce those actually by 9 each. So you got a 1/4 probability. Now, another thing they like on these is the 2 dice is what is the probability of getting sums. So let's just do the sum of 9. What's the probability of getting a sum of 9? Well, same concept. We just want it to be a sum of 9 here, and so how could we get a sum of 9? 6, 3. But again, 3, 6 is a different roll because of the first and second ones. 5, 4. 4, 5. I think that's it because, yeah, we don't have 7s and 8s. We're just talking about a regular pair of dice. 6 is the top number we can get. Now, sometimes on this it gets a little confusing because, so the top sum we can have is a sum of 12, right? 6 and 6. Well, that really doesn't play any kind of factor here. The probability that we get a sum of 9, we've got 4 possibilities out of how many? 36 still, yeah. We're still talking about the same 36 possible outcomes. Even though there's some of them in the same sums, that we still have 36. We're still counting all 36 here, possible outcomes. So that's still 36, still the total possibilities. So that reduces, got 1 out. All right? All right, now, let's talk about something else. Let's drop down to let's say we roll a single die. So just one of the things in the dice, just one of the cubes, if you will. Roll a single die. And, we could get some regular probabilities, but let's talk about some kind of special cases here, all right? So, number one, what is the probability of rolling a 7? Well, we're just rolling a single die here, so the possibilities are 1, 2, 3, 4, 5, or 6, right? We can't get a 7. So what does that make the probability of 7? If we were talking a pair of dice, we could roll a sum of 7, but we're just rolling a single one, so we can't get a 7. Well, how many outcomes are 7? 0, right? 0 out of 6? What does that simplify to be? That's just 0, yeah. If you have an impossible event, like rolling a 7 on a single die, that's impossible. The probability of that is always 0. If you've got an impossible event, the probability of such a thing is 0. All right? Number 2, let's go kind of the other end of the spectrum here. What is the probability we roll a number less than 7? Well, that's kind of the flip side of this, isn't it? The probability that it's less than 7, well, the outcomes again are 1 through 6. All of them are less than 7, aren't they? 6 out of 6. What does that simplify? That is 1. So that's the other side of things. Now, are we going to be able to get, would you say, less than 0? Is there a probability that's going to be less than 0? No. Is there going to be a probability that's greater than 1? No. The top number cannot exceed the bottom number here, if you think about it. So there's no way I can get a probability less than 0 or a probability greater than 1. So keep that in mind when you're doing these probabilities. You cannot have, this is also, that's a certain event. In a certain event, the probability is always 1 or 100%. So you can't have a probability that is less than 0 or greater than 1. So if you've got a probability that's outside of those ranges, the probability is not correct. Okay, because you can't have a probability less than 0 or greater than 1. So what does that mean? As far as what numbers we can't have, well, if you can't have less than 0, probabilities can't be negative. That's what it can't be less than 0. You can't have negative probabilities. And again, like I said, you can't have a number like a probability like 1.25 or 6 out of 5. Something like that. So you can't have a probability that's negative a half. You can't have a probability 6 over 5 or 1.25. Those aren't good probabilities because those are all outside of the range of probabilities. Most of them are going to be somewhere between 0 and 1, right? What we saw on all the other probabilities we've done to this point is between 0 and 1. So most of them are going to be between 0 and 1, but sometimes they are 0 and sometimes they are 1, but nothing outside of those. All right. Now, another thing let me mention here is what we've been finding so far is a theoretical probability. theoretical probability. Those are, we didn't call it that, but what we're talking about is theoretical probability. In other words, it's the probability in theory, because like the flipping the coin one. Did we actually flip a coin to say the probability of heads was 1/2 or 50%? When we're talking about flipping one coin. All right, so we flip a coin, the probability of heads is 50%, or 1/2. That's theoretical because I didn't actually flip the coin. I thought about what the coin has. It's got heads and tails. So that's in theory what it is. All right, so if you actually do some sampling or whatever you want to call it, an experiment, that's an empirical probability. All right, so that's a probability based on data or performing the event or on data, like I said, I think one of them in the book has it based on some data. That's an empirical probability because it's based on actually doing something. Empirical experiment, kind of tied in with experiment. So just to give you an example of that, all right, so let's say, use our flip a coin. Let's say we flip a coin 30 times and get heads 16 times. What's the empirical probability? What is the probability we got heads in this experiment here? Something like that. Well, based on the data here we have, the probability we got heads was, well, we had 16 successes for heads out of 30. So you see that's going to be probably a slightly different number than the theoretical probability of heads because it's based on the data. That does reduce 8/15. Is that right? The decimal, if you want to do the decimal. So you see kind of the difference there between those two. So if we wanted to, we could say empirical probability. What that is, empirical probability of event E. That is slightly different. I mean, it's not totally different, but so the probability of event E would be the number of times E occurs divide that by the total, again by the total number of occurrences or outcomes or data. So it's very much related, very much related. All right, now, just make a small little point here. Will the empirical probability match the theory? So if I said, all right, get a coin out and everybody flip it 10 times, is everybody going to get 50% heads? No. Okay, so usually empirical probability is not going to match the theoretical probability because of, chance things happen. So what can we say about it? I mean, we would expect it in most cases to be close. So empirical probability is probably going to be close to the theoretical probability. But, on certain occasions, if I flip a coin 10 times, 9 times are going to come out tails. Not very often, but sometimes it will. So the empirical probability will sort of match the theoretical. Now, the thing we like to say, though, is how can we kind of guarantee more the empirical matching the theoretical? How could we get those two to match up better? Probably do it more often, right? So instead of doing the flipping 10 times, if I do it 100 times, the empirical would more match the theoretical. So the more times you do something, the closer the empirical would be to the theoretical. So, like I said, just a little point, small little point there, but just be aware. Any questions or concerns about that? So it's basically the same. You just base it off data.